You are once again in the Greens Academy for lesson 2 of this chapter. That is the chapter of enzymes, or you can simply call it enzymology. Now, before we get into lesson 2, it is important for us to make a flashback on what we discussed in lesson 1. In lesson 1, we gave the objectives. We defined enzymes, where we said they are biological catalysts that speed up chemical reactions and remain unchanged at the end of the reaction. We also showed the importance of the shape of an enzyme, because we said that an enzyme's shape is determined by the sequence of amino acids in its structure and also the bonds that hold the amino acids together. The shape is also important because the substrate must be in conformity to the shape of the enzyme. We also talked about enzymes specificity. This is extremely important because if we do not understand this concept of specificity of enzyme, we will not understand other things that may come up in lessons ahead. Because enzymes are specific to particular reactions they carry. An enzyme that catalyzes a reaction B will not catalyze reaction A. That is why we gave the following example with the following enzymes. We said that the enzyme amylase can only catalyze the conversion of starch to glucose, while the enzyme maltase can only convert the conversion of maltose to 2 glucose molecules. So the enzyme amylase cannot carry out the reaction that is supposed to be carried out by maltase. So that is where specificity comes in. So it is good for us to understand this, that on an enzyme molecule there are active sites. There are active sites into which the substrate fits. The substrate that has the same shape to that of the active site. And all these lead to enzyme specificity. Now for lesson 2, we ask ourselves the following question: what happens at the active site of an enzyme? What happens at the active site of an enzyme? We have explained what is meant by the active site. We have said that the substrate binds to the active site. Now the question is, what happens at the active site of an enzyme? In the same way that a key fits into a lock, so a substrate fits into an enzyme's active site. This is very important because we are trying to make an analogy between the lock and the key and the substrate and the enzyme. When you take a lock and the key and you insert the key into the hole found on the lock, you are either opening the lock or closing the lock. And the key must conveniently fit into that hole. Therefore, You cannot take the key of another lock and open another lock. And this same aspect is carried out in enzymes activities. That is why we say that so the key fits into a lock, so the substrate fits into the enzyme's active site. You can, in your own, get a lock and a key, get two locks with two different keys. You take the lock of the key of a particular lock, open the lock, take the same key to open the other lock. You will realize that that key will not be able to open the other lock, because that key is meant to open just a particular lock. In other words, the key is specific to the lock it was fabricated for to open. That is why enzymes are specific to particular substrate. The enzyme is the lock and the substrate the key. The enzyme is the lock and the substrate the key, because the substrate is the key because you take the key and fit into the lock. Therefore, the substrate fits itself into their enzyme's site or active site. An enzyme binds on a substrate to produce a product. An enzyme binds on a substrate to produce a product. This is already what is happening at the active site, because when the substrate binds to the active site of the enzyme, a product is formed. Now, the first thing that is formed is called the enzyme substrate complex. This enzyme substrate complex is short-lived. It's short-lived. It means that immediately it is formed, it is now transformed. Immediately it is formed, it is transformed. It doesn't stay at that level because it has to go a long way to form the enzyme product complex, which is also short-lived. Once a reaction has occurred, the complex breaks up into products and enzyme. And at this point, the enzyme remains unchanged at the end of the reaction and is free to interact again with more substrates. And is free to interact again with more substrate. This is very important because we just said a few minutes ago that when a substrate binds to the enzyme's active site, a product is formed. The first thing that is formed is what we call the enzyme substrate complex, which is short-lived, which is later on converted to the enzyme product complex, which is also short-lived, and at the end of it, the product now leaves the enzyme's site, and the enzyme now becomes free with its active site, ready to catalyze another reaction. When you look at this diagram, it gives you a summary of what we have been talking about. You have 4 different diagrams here. The first one shows the structure of the enzyme and the structure of the substrate. You can now see that the substrate is green and the enzyme is brown. E stands for enzyme and S stands for substrate. You will now see that the substrate can conveniently bind to the active site of the enzyme because they have the same shape. In other words, the shape of the substrate is in conformity to that of the enzyme. That is why diagram 2 shows us that the substrate is already fitted in the enzyme's active site, and an enzyme substrate complex is formed. This enzyme substrate complex is short-lived. Diagram 3 shows that the enzyme product complex is formed. Immediately the enzyme substrate complex is formed. The enzyme product complex is formed, which is also short-lived, and this leads to the fourth diagram that shows that the product now is released, or the product leaves the active site, leaving the active site of the enzyme free for it now to accept other substrate to start other reactions. So that is how you have to understand this diagram. The next diagram gives us a global summary of all what we have been talking about. It is also showing us how specific enzymes are. So if you look at it, you will realize that the substrate has the same shape to the enzyme's active site, and it can bind conveniently to the enzyme. And you see that the enzyme is carrying out some kind of cyclic reactions. When the substrate binds to the enzyme, an enzyme substrate complex is formed, which then leads to the formation of an enzyme product complex. And when the product is released, you now see an arrow showing that the enzyme is free with its active site, ready now to accept other substrate to start a new reaction. Now, we now move to the next heading, which is also a question. Why do enzymes speed up reactions? Why do enzymes speed up reactions? This is a very important question. This is a very important question because from the definition we gave at the beginning in lesson 1, where we said that enzymes are biological catalysts that speed up chemical reactions, we need to understand why they speed up chemical reaction and how they speed up those reactions. Enzymes speed up reactions by lowering the activation energy. Enzymes speed up chemical reactions by lowering the activation energy of the reactions they catalyze. Now, how do they lower this activation energy? And what is an activation energy? Because we need to understand this. The activation energy is the energy needed to start a reaction. The activation energy is the energy needed to start a reaction. Therefore, without this energy, a reaction may not occur. Without this energy, a reaction may not occur. I'm going to use some examples to get you to understand exactly what is meant by an activation energy, or why is an activation energy required for a reaction to occur. Now, if you take oxygen and petrol, that is fuel, and put together, no reaction will occur. For a reaction to occur between oxygen and petrol, which is fuel, there must be a spark. Without the spark, no reaction will occur, because it takes a spark to occur for flame to be generated or for fire to come. Because that spark now is required for a reaction to occur between oxygen and petrol, which is fuel. I will make another example here between a box of match and a stick of match. If you take a box of match and a stick of match and put together, there will be no reaction. No fire will occur, or no flame will be generated. Because you need to take the stick of match and scratch on the box of match for a spark to occur, for fire to come up. So you need that spark for the flame to be generated. Without the spark, there will be no fire to occur on the stick of match. Therefore, what are we trying to say? We are trying to say that for fire to occur when there is oxygen and petrol, or when there is a stick and a box of match, there must be a spark. Therefore, the spark now serves as the activation energy. It needed that spark for fire to occur between petrol and fuel, or the box of match and the stick of match. So that is how you can understand this concept of activation energy, that activates, which is required for a reaction to occur. Since enzymes are catalysts, they serve to reduce the activation energy required for a chemical reaction to occur or to take place. They speed up the overall rate without changing to any great extent the temperature at which it occurs. Again, I don't want you to get confused here, because we just said a few minutes ago that enzymes lower the activation energy of reactions. And now we are saying here that they do all that without changing the temperature at which the reaction occurs. So it is better for us to understand this, that they are there to speed up chemical reaction by lowering the activation energy, but they don't change the temperature at which the reaction occurs. Now, this diagram summarizes what we have been talking about, activation energy. How important they are when enzymes are involved. When you look at this particular diagram, you realize that we have two graphs. The first graph with the highest peak is blue, and the second graph with the lower peak is green. Now, you realize that in this diagram, you have a substrate, which is a glucose molecule. You have 6 molecules of oxygen up there. that's about to oxidize the glucose molecule. Therefore, this is the reaction of respiration. So you now realize that in this reaction, the first graph, which is in blue, has a peak that is higher than the second graph, the green graph. So with the first graph, the blue graph, no enzyme is involved. No enzyme is involved. And that is why the activation energy in this case is very high. The activation energy is very high, and the reaction occurs so slow. In the second graph, you have, which is green anyway, you have a lower peak. In this case, enzymes or an enzyme is involved, and in this case the activation energy is low, and the reaction occurs very fast, or occurs faster than the first one, because an enzyme is involved in the second reaction of the green graph, and the enzyme here had to lower the activation energy, and the reaction occurred faster than the first one. In the first one, which is the blue graph, no enzyme was involved, and the activation energy was very high, and the reaction took longer than the second one. The second one, the enzyme was involved, the activation energy was low, and the reaction occurred faster. Though both reactions lead to the same products, the second one is faster than the first one, that is that of the blue graph. So that is really the summary, showing how enzymes speed up chemical reactions by lowering the activation energy. In this particular reaction, at the end of it, you have 6 molecules of carbon dioxide produced, 6 molecules of water produced, and energy that is generated, which is simply the reaction of respiration catalyzed by the enzyme, in the case where an enzyme is involved. So that is it. Because many students get confused when they get to such diagrams, and to interpret it is another problem. So just understand the function of enzymes in this particular case with the activation energy involved, and you realize that where enzymes are involved, the activation energy is low, and where enzymes are not involved, that is the case of the blue graph, the activation energy is high. So that is it for this lesson. I hope you enjoyed it, and we just need to prepare ourselves for the next lesson, which is lesson 3.